starting today, we're working on logarithms. So we're in section 7.5. This is the last part of chapter 7. We're almost half done the course. This is booklet 1 of 2. We're just going to finish up this last little bit. We're going to start something completely new after this chapter. That'll be chapter 8. Will be totally new. Chapter 7, logarithms. This should, again, be like review from high school. So if you had a good high school class, you probably did logarithms in a lot of detail. This will feel very reviewy. If you've never done logarithms before, it's going to feel fast. And you should feel like you should do a lot of practice problems. I put some practice problems on the homework. I didn't want to make the homework due today because we just had the midterm. I couldn't make the homework due next Monday because that's reading week. I didn't want to make it due the Monday when we get back from reading week because that's also annoying. So I put it on the Friday after reading week is the homework for all of the chapter 7 stuff. So lines and quadratics, not this Friday, but 2 weeks from Friday. You have a long time to do it, so hopefully you can take a nice break and do that. Okay, but that being said, we're doing logarithms. And what are logarithms? I'm trying to convince you with these 2 questions, we're going to do this one and one more like it, that logarithms are the exact same as exponentials, but we're just filling in a different blank. So with an exponential, you normally fill in something like this. 3 squared equals blank, right? That's what you normally do with exponents. 3 to the power 2, what is it? That exact information, 3 to the power 2, what is it? That is also a logarithm. And that's what this equation is going to show us. But let's start with this one. 10 to the power blank equals 1,000. What is the blank? What is the blank? 10 to the power blank equals 1,000. If you said 2, you're wrong. 10 to the power 2 is 100. 10 to the power 3 equals 1,000. This happened to me at the 230 class as well. A bunch of people put 10, and I cannot figure out why you would put 10. There must be a reason you would put 10. 10 to the power 10 is 10 with 10 zeros. 10 to the power 10 is like 1,000 billion or something. Wait, a billion is how many? 1,000 is 3 zeros, a million is 6 zeros, a billion is 9 zeros. 10 to the 10 is 10 billion. So if you put 10, you were off by a factor of 100 million or something. I don't know why 10 is such a popular answer. Lots of people pick 10 at 230 and also at this class. But the answer is not 10, it's 3. 10 to the 3 equals 1,000. About half the people got that. Okay. 10 to the 3 equals 1,000. 10 to the 3 equals 1,000. A logarithm is just expressing that 10 to the 3 equals 1,000 in a different way. So the way you would express it with exponents is you would write 10, you would write the exponent 3, you would say equals 1,000. With a logarithm, you say the log base 10 of 1,000 is what? It's 3. It's 3. Okay. Only 35 people got it right. 59 people and 55 people. So if you put 10 for both, that's at least consistent. It is supposed to be the same thing in both, but that number is 3. Okay. So let's fill this in the notes. There's a blank for this. This is taken directly from the notes. On the next page, finding the notes. So this is exactly what a logarithm is. I'm on page 262 in the notes, right? If you fill in the blank on 10 to the blank equals 1,000, the blank should be 3. The exponent is 3. The exponent is 3. Exponent is 3. The base is 10. The base is 10. Let's do base. Blue for base. Base is 10. The exponent is 3. Do any colors start with the letter E? No. So the exponent is 3. The base is 10. And so the way you would write this as a logarithm, it's the same piece of information. You put the 10 down here. You put the original number here. And you write that it's equal to 3. The exponent is there. So logarithms are equal to the exponent of whatever you would take the base to. That is one of them. Here is another one that we did. We did this one with 3 squared. We did option 2 as well. And in this one, you were told that the exponent is 2. So somebody told you already that the exponent is 2. They told us that the base was 3. And then you were supposed to calculate what is 3 squared. And hopefully everybody got that one. 3 squared is... Yay, 90% of people got it. It's 9. People who are putting in 1. I don't know what's going on. I don't know why you would think it's 1. Okay, 3 squared is 9. 3 squared is 9. So there we go. And if 3 squared is 9, how do we express this same exact piece of information? 3 to the power 2 equals 9. How do we express that with a logarithm? The log of the base 3 of what? Of the number of the 9 is equal to the exponent. So the output of the logarithm is always the exponent, and the input is the number, what we are finding. So I'm writing the number here in red. Okay, so logarithms are secretly just exponentials in disguise. How many people got this one right? The log base 3 of 9. Less people. Some people got bamboozled by this one. Okay. Log base 3 of 9 is 2 is the same as the fact 3 squared equals 9. So logarithms just express facts about exponentials in a new form. And the definition is written here. So if you want to read the exact definition, here it is written all abstractly. Right? So I gave names to all these things. Y, I called that the number. The number. The number is the log of base b of the base, and here x is the exponent. The exponent. I have it backwards. The number is the thing on the inside, and the thing that you're equal to is the exponent. Exponent. And here is the number. The number. And that's the same thing as b to the power y equals x. B in blue to the power y in red is equal to x in pink. Nope, I got it backwards. Right? Y is the exponent. Y is the exponent. I keep saying it out loud and then writing it down wrong. All right. The number. Okay. So we're expressing exponents by having the output be what is the exponent. Y equals the logarithm. Y is the exponent. Here's 3 more for you to do from this table. If you want, you can try to do the whole table and see if you're right. If you know logarithms, it should be a breeze. Let's do exercise 2. Exercise 2. And I'll give you 2 minutes to try this one. Okay, there's like 15 seconds left. Put in your final answers. Okay, let's take a look at what you guys said. So 4 to the power blank equals 64. So you see 64. 64 you should definitely see as a multiple, or a power of 2 rather. It's a power of 2. What is it? You know the N64, right? No, maybe that was before your time. The N64, because it has 64 bits, it's a power of 2. Okay. So 4 to what power? Well, you have to double a bunch of times. How many times do you have to double? Let's see if you guys know. 4 to the power 3. That is correct. If you said 3, very good. And if 4 to the power 3 equals 64, what power do you need to raise 4 to get 64? The answer is 3, and that is also the logarithm. What power do you need to do it? It is 3. So great job, guys. Almost everyone got that right. Somebody did the actual computation. That's not what we want. The answer is 3. OK, good. Let's do this one. This one is even easier. What exponent do you raise 5 to get 5 to the 3? You don't even need to know what 5 to the 3 is. This could have said 5 to the 3,000. The answer is just 3. It's 3. 5 to the 3 equals 5 to the 3. Welcome to the tautology club. Tautology just means it's a true thing because it's true, so we're not saying anything. So 5 to the 3 is 5 to the 3. Well, that tells you that the log base 5 of 5 to the 3 is also 3. Oh, less people got this one right. So maybe this one was confusing? Yeah, it's 3 because 3 was the exponent. Whatever the exponent is, that's what the logarithm is equal to. So let's go fill these in on our notes. So which one did we just do? 4 to the power what? 4 to the power 3 is 64. And that means that the log base 4 of 64 is 3. 5 to the power what is equal to 5 to the 3? 5 to the power 3 equals 5 to the 3. And therefore, the log base 5 of 5 to the 3 is 3. This works for any base. The log base 5 of 5 to the 1, 2, 3, 4, 5 is equal to 1, 2, 3, 4, 5. And that is because what power do you have to raise 5 to get 5 to the 1, 2, 3, 4, 5? It's 1, 2, 3, 4, 5. It's sort of like self-explanatory. Like this fact is sort of by the definition of the logarithm, this has to be true. We're just unpackaging the definition. OK, there's a couple more on here. Let's do the rest of them. Here's an interesting one. 5 to the power 0. We did this one in class last time on exponentials. Anything to the power 0 is 1. Anything to the power of 0 is 1. And that means if you do the log of any base of 1, the log base 5 of 1, it's going to be the exponent. Whatever is in the exponent, that'll be the answer. That's 0. So the log of 1 is always 0. The log of 1 is always 0. Here's one more with some funny negative signs to trip you up. 1/3 to the power negative 3. Well, 1/3 is 3 to the power minus 1. Reciprocal is a power minus 1. So we have 3 to the power minus 1, all to the power minus 3. The exponents multiply. You get 3 to the negative 1 times 3. That is 3 cubed. 3 cubed. And 3 cubed is 27. 3 cubed is 27. So 1/3 to the negative 3 is 27. And that means if you do the log base 1/3 of that number, of the number 27, you get, what do? You get the exponent. And the exponent is negative 3. So the log base 1/3 of 27 is negative 3, exactly because of this fact about exponentials we just figured out. So logs and exponentials, they're the same thing, just written in a different format. The output is the exponent. The thing is the exponent in pink. It's not written upstairs, it's just written out. The log is the exponent. That's what a logarithm is. And you might have noticed, like, we already have a lot of rules for exponents, right? Like, this was a rule of exponents from the high school algebra test. Multiplying the exponents whenever you do the exponent of an exponent. And because of that, we have rules for logs. So we can deduce the rules of logarithms from the rules of exponents. So I'm going to give you the two big rules. One is, if you multiply numbers, multiplying numbers is the same as adding the exponents. So for example, if you do 2 to the power 3 times 2 to the power 2, you're multiplying the numbers, 2 to the 3 and 2 to the 2. You add the exponents. This is 2 to the 3 plus 2 to the 2. 2 to the 3 plus 2. And this translates, multiplying numbers is the same as adding exponents. This translates into a rule for logarithms, which is this called the product rule over here. And it says that if you do the logarithm of a product, so you multiply the numbers, multiply numbers, then on this side, you are adding the exponents. Adding exponents. And remember, the logarithms tell you the exponents. So when you're adding the exponents, that's adding the logarithms. This rule, the product rule, is exactly the same thing as the thing I wrote before. 2 to the 3 times 2 to the 2 is 2 to the 3 plus 2. This multiply sign over here, this multiplication, it turned into addition up here. Okay? And the same thing happened over here. Multiplication inside here, m times n, turned into addition outside the logarithm. It's the exact same fact written in two different ways. Once with exponentials, once with logarithms. The same thing works for ratios. So dividing numbers, that turns into subtracting exponents. And to give you an example, you could do 2 to the 3 divided by 2 to the 2. That would be 2 to the 3 minus 2, also known as 2 to the 1. So dividing the numbers turned into subtracting the exponents. It's the same thing with the logarithms. dividing the numbers turns into a minus sign. Last but not least is the power rule, which says that taking a powers, that becomes multiply the exponent. And so the example I'm going to give you is if you do 2 to the power 3, 2 squared all to the power 3, you're going to multiply that 2 and that 3. So 2 to the 2 times 3. And so this becomes a multiplication. Over here it is a power, and over there it's a multiplication. In the exponent, multiplication of the number, powers of the number, became multiplying the exponent. And logarithms do exactly that. You can also think of this one in a fun way of the power p is jumping down to be in front and to get this thing on the right-hand side. Okay, last but not least, there's another rule, and this is the same as the rule for exponentials we had, which says that if the logarithms are equal, then the numbers must have been equal. We used that for exponents before. We said if 2 to the x equals 2 to the 7, then x equals 7. It's the same rule, but written in terms of logarithms, it means exactly the same thing. Okay, so these are a bunch of properties. Now we are going to apply these properties to do some simplifications. Let's do this. Did I write the thing down? Yeah, okay. Okay, so here we go. We're gonna apply these to do some simplifications. So here are some simplifications. There's the log base 3 of 243. And let's pretend you didn't know anything about 243 and you didn't have a calculator and you wanted to figure out what is the log base 3 of 243. This is like a problem, but one thing you can do is you can try to make this number smaller by doing this. I'm going to write it as the log base 3 of 3 times 243 divided by 3. So I'm just going to try to divide it by 3 and see what happens. And this will help me because by the logarithm rules, multiplying by 3 is the same thing as adding the logarithm. So by the rule that multiplying inside becomes addition outside, it became addition outside, I can simplify this thing to be this, 243 divided by 3. So basically, I can take my number, 243, and I can make it smaller by a factor of 3, and now I have smaller numbers to deal with. And by the way, what is the log base 3 of 3? I know how to do that one. This is 1. Why is the log base 3 of 3 1? This is similar to what we did before. You could say it's because 3 to the power 1 equals 3, right? 1 is the exponent you raise 3 to get 3, so the log base 3 of 3 is 1. So that's 1. I got to add it on to what? 243 divided by 3 is something you can do. You can try to do long division. This is almost like 240 divided by 3. 240 divided by 3 would be 80, and we have 3 extra, so that's 1 more. So that's the log base 3 of 81. So I did all this stuff to just try to make the number smaller, and now I turned a 243 into an 81. I could do it again. If you do it again, and maybe I'll skip some steps. If you do it again, you get another 1 plus, and then you divide the thing by 3 again. So you get the log base 3. You'll get the log base 3 of 81 divided by 3. If you do it again, what is 81 divided by 3? That's 27. This is 27. And now I'm starting to recognize this as a power of 3. We have 27. I know that 27 is 3 to the power 3. We did that earlier. So this is 1 plus the log base 3 of 3 to the power 3. And I recognize that as 3. So it's 1 plus 3, which is 5. So I could have done the whole thing by trying to figure out what power works to get 5, but this way I use the log rules. You can see that a division by 3 inside the logarithm is the same as a plus 1 on the outside. That's what I was trying to show you. And by doing this, you can figure out the logs of all sorts of things. Okay, here's another example, right? Part B says do the log base 2 of 128 and the log base 2 of 4 and subtract them. So of course you could treat this as 2 separate problems. First do one, then do the other, and then subtract them. But it's easier if you treat it as one problem and use the log rules to simplify. And the log rules to simplify say that if you have a minus sign on the outside, that turns into a divided on the inside. So a minus sign on the outside will be the same as a 128 divided by 4. So subtracting the logarithms is the same as dividing the original numbers inside. And what is 128 divided by 4? 128 divided by 4, that's like dividing by 2 twice. That's 32. Okay. What is the log base 2 of 32? 32 I recognize as a power of 2. You got to double it how many times? 2, 4, 8, 16, 32, 5 times. So 5. This is 5. 32 is 2 to the power 5, so the log base 2 of 32 is 5. Okay, here's another one. Part C, log base 5 of 25 squared. By the power rule, this 2 in the exponent jumps down. So this is 2 times the log base 5 of 25. The 2 in the exponent just jumps down. It simplifies. It just doubles whatever we get. What is the log base 5 of 25? Well, that's also 2 because 25 is 5 squared. So this is 2 times 2. So final answer 4 for this one. And let me try to draw the dotted line separating these guys again. Okay. Okay, one more. We have an annoying 1 over 8. How do we deal with things like 1 over? Well, we turn them into powers. That's 8 to the power negative 1. And a power like negative 1 jumps down by the power rule. The power jumps down by the power rule. This jumps down. So you get negative 1 times what? The log base 2 of 8. 8 is 2 to the power 3, so that's a 3 minus 1 times 3, also known as minus 3. So there you go. We did that one. Okay, one last one. How do I deal with a cube root? A cube root, just like a reciprocal is a power, a cube root is also a power. This is 64 to the power 1/3. And the 1/3 is a power that jumps down. So we get 1/3 times the log base 8 of 64. And 64 is 8 squared, so that's just 2. 1/3 times 2, also known as 2/3 for that one. So you can see, by using the log rules, you can do all sorts of logs, even if all you know is like really basic things, like 64 is 8 squared, and 243 divided by 3, that's stuff like that. Okay. That was an example of using the log rules to simplify some stuff. In a second, we're gonna learn a new fact about change of base, and then we're gonna start doing some harder ones that are similar to this but have x's and stuff in them, or have more algebra rules in them. Are there any questions and comments about just the pure number version before we move on to the same thing but with algebra? Okay, so let's see. So here are some more facts that we're going to throw at you about logarithms. So here are 2 facts you got to just memorize. When someone writes a log and they don't write a base, they forgot to write the base, they mean log base 10. So log with no base is log base 10, logarithm to the base 10. What if they write this funny thing, ln? What is ln? Well, you're supposed to just memorize ln means log base e. So the base is e, and that's called the natural logarithm, and you read it out loud as the word lawn. So the way I remember it is you get off my lawn because my lawn is so natural. Maybe a dumb way. E is the special number, 2.718 ... It turns out E is really important for exponentials for a reason we're going to see when we do exponential growth at the end of today's class. If you have this base E, there is another fact that is useful. You can turn everything into only ever using ln. So some calculators have a ln button and don't have any other logs. They only have ln. And by using the change of base formula, you can change anything to be a ln. That's done on the next page. And they give you an example. So here is, if you want to do, suppose you wanted to do the log base 3 of 5, but oh no, your calculator doesn't have a log base 3 button. Your calculator only has an ln button, a ln button. Well, you can do the log base 3 of 5. It's going to be the ln of 5 divided by the ln of 3. So you put ln of 5 and ln of 3 in your calculator, you get these numbers, 1.609 and 1.098. You divide them, and you get the number you were looking for. So that's called the change of base formula, and it also works like this. The log of the old base of some number is the ratio of the logs in the new base, the ratio of the log of the number to the log of the old base. So this is called the change of base formula. Sometimes it's useful. Useful for calculators if you only have the buttons for base E and base 10. Okay. The useful fact about logs. Now we're going to start doing some harder ones with x's. Here is the first one. Can you do the equation, solve the equation 5e to the 2x equals 7? And this is a good one to try. It doesn't translate well into mathematized, but I'm nevertheless going to give you guys a couple minutes to try it. So if you can get to x equals and fill in something over here, and you can do it, then you are good at logarithms. If not, you will need to practice logarithms. I'm going to give you 2 minutes to say do it. Yeah, let's do 2 minutes. Okay, so let me show you how I would do this problem. There's lots of ways you could do it. The first thing I'm going to do is divide both sides by 5 to get e to the 2x is 7 over 5. And that's because I want to get the e to the 2x on its own. And now that I have e to the 2x equals 7 over 5, this is the same expression. You're right, I have a base. The base is e. I have an exponent. The exponent is 2x. And I have a number that it's equal to, which is 7 over 5. So I have a base, an exponent, and a number. It's written in the exponential way. But of course, you could equally well write this exact equation in the logarithm way. So we're going to rewrite as a log, write as log. And in this case, it's the log base e. It's the log base e. So anytime you have an equation with an exponent, it has an equivalent equation with a log. This is the log base e, also known as the ln. What is this equation? Base to the power exponent equals number. It turns into the logarithm base e of the number. What is the number over here? It's 7 over 5 equals the exponent. Okay, let me make this black, and then I'm going to make e, that was supposed to be green, e, and then this one is the exponent. The exponent is in pink. So the equation e to the 2x equals 7 over 5 is the same exact equation as the log base e of 7 over 5 equals 2x. Those are the same thing, they mean the exact same thing. So I've converted from an exponential into a logarithm by doing that, by just rearranging what is the base, the number, and the exponent in the right way. And the log base e is the same as the ln. So you might see this written as the ln of 7 over 5 is 2x. So if I have an equation for 2x, how do I get the equation for x? I just move the 2 to the other side. So this is 1/2 times the ln of 7 over 5. So that's one way to do it, using the definition. I will say another common way that people do it, this is a little aside here, this is an alternate solution. One thing people do is they take the log of both sides, which is a great idea to do. And if you take the ln of both sides, you get ln of e to the 2x equals ln of 7 over 5. So this is an alternate way you could have done it. Instead of doing what I did, you could have taken the ln of both sides, ln of e to the 2x equals ln of 7 over 5, and now you use the power rule to get that 2x times the ln of e equals the ln of 7 over 5, right? And this was the exponent rule that the 2x jumps down in front. And now the ln of e, what power do you have to take e to get e? It's 1. So ln of e is 1. 2x equals the ln of 7 over 5, and now you can divide by 2 to get the same final answer. So that's an alternate way to do it. This was like method 1 over here, method 1, and this was method 2, and both of them are completely the same. Do whichever you prefer, whichever you like better. Okay. Questions or comments about that one? Okay, let's do one more. Here, I'll save this for people who are still copying it down. Here's another one that I'm going to do. The log base 3 of x equals all this stuff. Find x. And of course, one way you could do it is you can just put this in your calculator, get some crazy decimal, and then do it that way. But I'm going to try to simplify this first using the log rules. And so the first log rule I'm going to use is that this exponent, or this multiplying by 1/3, that can jump into the exponent. So far I've only ever used it the other way. Now I'm using that power rule to put the exponent 1/3 back in. So the log 3, 8 to the power 1/3. And now I can use the product rule because I'm adding the logarithms. And when you add the logarithms, that is multiplying the actual numbers. So this is 5 times 8 to the 1/3. So far I've used the power rule once to deal with the multiplying by 1/3, and I've used the product rule to deal with plussing logarithms is the same as multiplying the numbers. So I'm finally at, after all these steps, the log base 3 of x is equal to the log base 3 of 5 times 8 to the 1/3. And now if the log of something equals the log of something, the two somethings are equal. This is the equality rule. So this means x equals 5 times 8 to the 1/3. Okay, and this is a perfectly fine answer. X equals 5 times 8 to the 1/3. Of course, if you want to simplify it, you might know what is 8 to the 1/3. 8 to the 1/3, also known as the cube root of 8. What is the cube root of 8? It's 2. So this is 10. If you want, this is 10. But you could have left it as 5 times 8 to the 1/3. This is an example of using the log rules to simplify an equation before you solve it. Questions or comments about that one? Okay, so on the next 2 pages, there are more examples, and they get harder and harder. So here is another one, solve for x. You know, there's some stuff with logs and x's. This time, there's logs and x's on both sides. This one is like the last one, but harder. And then the one after that is like the last one, but even harder. Okay, so they sort of get harder and harder using the same things. I don't think it's super instructive for me to just do some super hard problem and like do lines of algebra before you guys have a chance to do it. So the way you should learn this problem, you should try it yourself. Try it yourself. And I will post a video solution, and you can compare and see if you got it right. Then see solution. Because when a problem like this comes on midterm 2, that is what you're going to have to do. You're going to have it, you're going to try it yourself, and just watching me do it won't help you do it. Of course, if you're completely stuck and you get nowhere trying it yourself, then you could go watch the solution. At least you'll see like, where did I get stuck, right? Like you'll have an answer to that question at least. So it's a lot more instructive if you try it yourself first. I think it takes a while. This one's hard. You can't do it in just like 1 minute unless you're already very good and know logarithms already. So try it yourself, then see the solution. I will post a video, post extra video. I will do that. Okay, and I'm going to do that for both this exercise, 113, and the next one. But really try to come up with like x equals question mark, x equals what, and then see if it's the same as my x equals. Okay. Exercise 113 and 114, that is it for playing around with logs. In the next section, we're going to think of the log function as a function. By the way, before I start thinking of the log function as a function, any questions or comments about any of that log simplifying stuff? So in this next section, the log function is a function. It's the function f of x, which is the log base b of x. And what can we say about this function? Right? We spend a lot of time doing functions in general. Here is one function. What can we say? What is its domain? What is its range? How is it related to the other functions we know? And the first thing we're going to show you is that this function, f of x, is the log. And actually, let me not call f of x the log. Let me do it the same way they do it over here. Let's make f of x the function b over b to the power x. This is the exponential function we saw last class. This is the function that looks like this. It goes bloop, 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 and it goes up, 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 right? If you played it on Desmos and you hit the play button, it would go whoop, it would sound like that, right? It goes up, up, up. This is an exponential growth function. That's f of x. Actually, you know what? Okay, life is too short to miss opportunities to play fun functions out loud. If we're talking about this, we should do it, right? Let's do it. So here's the function. Someone yell out what should b be? What should b be? If I type in what should b be, it doesn't work. I need a value for b. 3, amazing. B equals 3. What a revelation. Okay, and now I'm going to do b to the power x. B to the power x. That's what b to the x looks like. It looks just like I drew it. And what do we say you got to do? You got to Alt-Shift-T. Alt. Anyone remember the secret shortcut? Command-T. Okay, now we got to Google how to do the secret shortcut because I don't remember. Alt F4, someone says. Thank you. Desmos, play sound for function. Alt-T. Okay, great. Alt-T. Command-T. Nope. Option-T. Ah, here we go. Okay, here we go. We're going to listen to it. That was anticlimactic. I want Option-T. Okay, here we go. One more time. I did a very good job of saying that out loud. I'm very proud of myself. Okay, that's that function. Now we know what that function is. Okay, b to the x. That's f. The point of doing all this stuff, that was an exponential. What are we doing in this class? We're doing logarithms. And the logarithm function is the inverse function. The logarithm is the inverse. So f inverse of x is the function, the log base b of x. How do you go from a function to its inverse? We did this in chapter 6. If the function is going up, to get the inverse, you swap the x and the y-axis, right? You do this like flipping around the line y equals x. So you got to take the function and flip it around y equals x. So it's going to look like this. It's going to look like that. What is it going to sound like? I don't know. That's why we did this, so we could find out. So I'm going to do the log base b of x. There it is in red. There's what it looks like. What does it sound like? That's what I wanted to know. So the exponential function is going up really fast, and if the exponential is going up really fast, then the logarithm is going up really slow. So it starts out quite slow. Can I do this in reverse? No. So it goes up a lot right at the beginning. It has this vertical asymptote at x equals 0, at y equals 0. No, at x equals 0, and then it goes nice and slow forever. Nice boring function, super slow. Okay, that's what we're doing in this class. We're learning how the function looks like, and it's the inverse function of the exponential. And if it's the inverse function of the exponential, you have these two properties that say f of f inverse and f inverse of f are just the identity function. If you do f of f inverse of a thing, you get back the thing. If you do f inverse of f, you get back the thing. If you do something and then you undo it, you get back to where you started. That's what this is saying. And this law is the same exact law as that. 2 just means that the inverse of the exponential is the log function and vice versa. Recall how to graph f inverse. You reflect the graph in the line y equals x. That's what we just did. Okay, very good. We've understood this inverse relationship. How do we test and make sure we understand this inverse relationship? We fill in these like 5 simple examples to make sure we know what's going on. What is the log base 2 of 2 to the 3? Logarithms undo exponentials. I did 2 to the power 3, then I undid it. What do you get? What do you get? You get 3. Torture 3 for a little bit, then untorture 3, you get back 3, okay? What if I do it to x squared? Let's do this one next, because I feel like it. Start with x squared, do something to it, and then undo it. What do you get? You get x squared. You did something, you undid it. The thing you did was an exponential, the undoing it was the logarithm. What about over here? 3 to the power log 3 of 9. First I did the logarithm, then I did the exponential. I undid a thing, then I did it. It's the same thing. You undo it, you get back what you started with, in this case 9. Okay. What about this one? This one has a trick in it. There's a silly 3 in the exponent ruining my day. How do I make the 3 in the exponent go away? I write the fact that a product in the exponent is an exponent of the original numbers. So I do 3 to the log 3 of 2 to the power 3. So that multiplying by 3 is the same as taking the whole thing to the power 3. And now that stuff in blue is doing something and undoing it. 3 to the log 3 of 2. Do the logarithm of 2, then do the exponential. That will just give you back 2. So it's going to be 2 to the power 3. Also known, as we've seen a number of times in this lecture, 8. 2 to the 3 is 8. Okay. By the way, there's another way you can do it, where you end up with 3 to the log base 3 of 8, which is also 8. So if you want, there's an alternate method. I won't tell you what the alternate method is. You can figure it out yourself. Okay. Exercise 116, fill in the boxes. If f is 2 to the x, what is f inverse? Well, we just told you it's the log base 2 of x. If f is e to the x, what is f inverse? Well, it's the log base e. The log base e. What is the log base e? That's the ln of x. If f of x is 10 to the x, what is f inverse? I think you see the pattern. It's the log base 10 of x, also known as log, don't write anything, log x. Okay, so now we know the function and its inverse. We're going to go back to the graph now. So I did a little super quick sketch of the graph. I played with it in Desmos. Let's do the graph in a little more detail. That is over here. Okay, and there's one more thing about it, increasing and decreasing. I'm going to go do this in a second. So we'll come back to this, come back to this. In fact, it's later on in the notes. It's written twice. But I want to talk about graphing it. How do you graph it? And the way you graph it is you take the tables for 2 to the x and 1/2 to the x, and you flip them. So if you remember last class, we had x and we had 2 to the x, and it went like this. It was like 0, 1, 2, 3, 4, and 2 to the x was the function that doubles. So it starts at 1, and then it goes 1, 2, 4, 8, 16. That was 2 to the x, the doubling function. And if 2 to the x is the doubling function, and if log 2 is the inverse, I just take those numbers, 1, 2, 4, 8, 16, those become the x values, and these things over here become the y values. So 1, when x equals 1, that's the same as this line over here, 0, 1, I put in the number 0. The log of 1 is 0. 2, that's this line. The log of 2 is 1, base 2. This line, 4, 2, becomes 2, 4. The log base 2 of 4 is 2. And last but not least, 8, 3 becomes 8, 3. There you go. The log is the inverse of the exponential. We take the exponential table, we just flip the columns, The inputs become the outputs become the inputs. That's what we have. What does it look like? Let's do the graph. Here's what it looks like as the graph. The log base 2 of x. Do you remember? I said we had this line, y equals x. Y equals x looks like this. Minus 1, minus 1, 1. Where's 2? 2, 2. Y equals x. 1, 1, 2, 2, 3, 3. Okay, well, it's this line. So if you take the exponential function looks like this. And then you flip it, you get the log function. It looks like this. That was this function. Okay. And this is the log base 2 of x. It's exactly what we had in Desmos. We did it with log base 3 there. This is log base 2. And look, it has this property. Right here is x equals 1. X equals 1. We double it to get x equals 2. We double it again to get x equals 4. And then you double it again to get x equals 8. And when you're doing this doubling, the y values go up by 1 every time. Plus 1, plus 1, plus 1. When you double the inputs, the outputs go up by 1. Logarithms turn doubling into addition. They turn multiplication into addition. That's the log base 2. What about the log base 1/2? Well, you might remember the graph of 1/2 to the x. It looks like the same thing going down. So 1/2 to the x looks like this graph, the exponential decay graph going wee all the way down to 0. And so log base 1/2 is the opposite of that. It goes all the way down, down like that. You take that graph going down, you flip the x and the y-axis, and that's what it'll look like. And you can do that with a table. That's done over here. So the table for the powers of 1/2, what were they? X, and what is 1/2 to the x? If you started at 0, you would get, when x equals 0, 1/2 to the 0 is 1, and then it was multiplying by 1/2. So 1/2, 1/4, 1/8 for 1, 2, and 3. And then if you go the opposite way, if you go -1, -2, -3, it was doing 2, 4, 8, right? The halving function in reverse is the doubling function. And that is why the logs for 1, 2, 4, 8 as inputs, you are reading off these 4 numbers over here. The answers are 0, -1, -2, and -3, reading off the numbers from the table for 1/2 to the x. So logs and the exponentials are inverses of each other. We can say that as a table. We can say that as a function. We can say that as a picture. We've seen it like 4 different ways. Any questions or comments about that? The next thing is, there's one more thing you need to know, which is increasing and decreasing. This is the thing I said I'd get back to. It's written on this line. The log function is increasing if the base b is bigger than 1. Log base b is increasing. And it's decreasing if b is between 0 and 1. You will almost never see this one. So if you're going to memorize one of these, I would memorize this one. This one is important. It's an increasing function. Its domain is all numbers that are positive, all positive numbers, positive only. And its range is all numbers. Okay, that's everything about the exponential function. We're going to move into what we want to get to. What we want to get to is something very special, which is this model on page 277. This is the exponential growth model. And this is like one of the most important models that you'll see in the world. It models things that grow exponentially. So things like bacteria, if it's doubling every so often, or uranium, if it's decaying every so often. Things that obey exponential growth, you write them like this. And there's 3 parameters. There's the parameter a0. Let me underline so they're not too obscured. There's the parameter a0, there's the parameter k, and there's the parameter t. What do a0, k, and t represent? Well, a0 is the initial amount of stuff. a0 is the amount of stuff at time 0. So if you're trying to figure out how much uranium is left in your mine, you figure out how much you had when you started, and then you see how long you waited, and that'll tell you how much there is. The other ingredients are the exponential growth rate, called k. It's the growth rate, which has the units of inverse time. So this is telling you what percent you move per time. We'll see an example in a second. It's the units per time. You should think of it as percent change per time. So if you double every week, then your percent change per week would be 100%. Percent change per unit time. Per unit time. Okay, and the last ingredient is t. T is the time. T is time. Time. So this is the exponential growth model. This is what we want to understand. Here's a picture of it. It looks like what you'd expect. It is an exponential that is growing. You start out with some amount of stuff. You start with A0 stuff at time 0. I think a good one is bacteria. So you start with bacteria in a petri dish. Maybe there's 1 million bacteria when you start your experiment. And then you wait a week, and a week later there is more bacteria, more. How much more? That's what the equation will tell you. So it's a very good model for these kinds of situations. And you need to understand these 3 parameters, A0, K, and T. Why am I telling you all this? The thing that is really important to keep your eye on, that I didn't mention at all, is that the special magical number E is appearing here. So this is E. E stands for Euler's number. Euler is a famous German mathematician. And this equation, this is the magical thing about E, this equation only works with E. The exponential growth model, if you change it to a 2, then K will no longer have the interpretation as the growth rate per time. So if you change it to a 2, it breaks. It doesn't work anymore. And for that reason, it's really important to be able to change your base to be E. That is what the point of this thing that I skipped was, changing the base to E. Why is that important? It's important because the base E is the best. The base E is the best. And this formula tells you how to do it. Here's the formula. B to the x is e to the x ln b. How would you write 7 to the x in terms of the space? Well, here b equals 7. And so if b equals 7, you get e to the x times the ln of 7. Okay, so what have we done so far? We've kind of introduced this exponential growth model. Next class, we're going to do some real problems with the exponential growth model. If you want to read ahead, I recommend you try this problem. This is a good one. You can try this. We'll do it next class. Try. Okay, see you guys on Wednesday.